So, ladies and gentlemen, dear colleagues, welcome to the 23rd installment of the scheduling seminar. And we have a pleasure to have a very famous speaker today. So I would like to ask Mike Pinedo to introduce him. But Mike maybe is muted. Sorry for that.
Mike, you are muted.
I ask him to mute.
Okay, yeah.
Now we hear you.
Okay, let me introduce Pascal van Hentenryck. He is originally he is a computer scientist, somewhere on the borderline between computer science and operations research. And he is actually a very good counterweight to the mathematical programmers. And his research, he uses constraint programming, and he likes to show us in a very, very pleasant manner how constraint programming dominates mathematical programming. And I'm fairly sure that and he makes a convincing case. By the way, it's not only in experimental research by academics, also by software companies that do optimization for industry. Apparently, constraint programming, we can still learn a lot from him. Okay, Pascal, go ahead.
Yeah, thank you, Michael, for a very nice introduction, and happy to see so many of you at this talk. So I'm going to talk about constraint programming for scheduling and branch a little bit at the end. And obviously, I'm going to advocate a little bit for constraint programming, but I'm also going to show you the kind of convergence that you see at this point between mathematical and constraint programming, which I think is probably the most interesting, exciting things that have happened in the last couple of years. So I want to go back 10 years or almost 12 years now. And this is the way I used to present talks about constraint programming. I would basically, quote these two magazines, which are both in computer science and in operation research, stating the value of constraint programming. And obviously that was, like 12 or 11 years ago. I typically was also using this slide for my trick, and my trick was using constraint programming and mathematical programming for solving big scheduling problems in the sport industry, in particular baseball and the NFL. And one of the things that Mike was saying is that the optimization had made so much progress that if you didn't know the latest technology, you couldn't solve the problem he was solving. And he was listing three different technologies that he was using heavily in baseball scheduling. And one of them was these combinations of constraint programming and integer programming. Now we'll talk about that again. It's going to be different from what Mike was talking about, but you'll see the connections today. So what I want to do is take those slides and tell you what has happened in the last 10 years, or some of the things which have happened. So I can't cover everything. But what I want to do is actually give you a couple of ideas that I think are important in the field right now. So I'll start with a brief overview of constraint programming, reminding you of the main concept and how they can be used for scheduling. Then I will give you the kind of applications that you can solve with the technology these days. And I'm going to use something in port scheduling, which is something that I'm really happy about because it took many, many years for actually getting there. But the applications now are very compelling in that field. Then I'll talk about this hybridization of constraint programming and mixed integer programming. Then I'll talk about this next generation of solvers, which are based on learning-based constraint programming. And then I will talk about machine learning at the end and how they can be used for in combination with optimization to solve some problems better than otherwise. Now, this is a lot of material, and the goal is not to go into all the technical details. I will give you papers to read if you're interested in some of them. But my goal here is to make you curious and to try to see what can be of interest to you such that you can go deep in some of these topics. Okay? Feel free to interrupt me if you have questions, obviously. So constraint programming is two things, right? So it's a very high level language for combinatorial optimization where you are trying to express the problem at a high level and reveal the structure of these applications. Typically, historically, you can program the search. You can still do that in some of the packages, but the progress that constraint programming solvers have been doing in the last decades has been essentially automating the search as you have in MIP solvers. So these days, you don't have to program the search. They are very good default search, and I'll talk a little bit about them later on. It's also a different approach to optimization, although once again, the boundaries between the two are blurring, as I will explain to you, but the focus is more on feasibility, and I'll come back to that at various points during the talk. So when you are, this is a slide that I'm always using when I teach constraint programming here at Georgia Tech. As you know, Georgia Tech is like this mathematical programming temple, and the students are taking some of my class after they have seen, mixed integer programming. And what I tell them is that, the first thing you need to do is forget everything that you have learned, because we are going to model in a completely different fashion, and we are going to solve the problem in a completely different fashion. And that's what I want to show you. So I want to show you that in the context of scheduling, which is one of the killer applications for constraint programming. I think, as Michael has said, this is heavily used in industry. And there are also a variety of problems in which MIP models face significant challenges. Not all of them. There are problems where MIP models are amazing in scheduling, but there are some of them where they face significant challenges. So when you think about scheduling, what the constraint programming systems are giving you is a modeling layers where we have very high level concept, and then you will have dedicated solving capabilities, both at the level of the constraint algorithm behind the scene, but also the way you compute lower bounds and the way you branch and the way you combine lower bounding and finding good primal solutions. So this is what you do in modern constraint programming languages for scheduling. You have this concept of an interval variable, which is like a one-dimensional object, if you want. So you have a start date, you have an end date, you have a duration, and all of which can be variables. And obviously, they are connecting by a constraint that says that the end date is the start date plus the duration. And so you basically have to choose. The decision variables here are finding the value for the start, end date, and durations. As I told you, the duration is a decision variables and can be chosen by the system as well when it does the search. So if you look at the Dropshot scheduling, which is like the simple example, what I want to show you is the level at which you present these examples. And so I think for this audience, I probably don't need to tell you what this is, but it's a set of jobs, sequence of tasks. Every task has a duration. One job can only execute one task at a time, and you want to minimize make span. And this is the data, for instance, for a small instances. And this is the level at which you model these problems in constraint programming. So you have these interval variables that I just mentioned. For every job and every task in the job, you have one of these interval variables, an activity in this particular case that I'm calling them. Then you have these sequence variables, and I will tell you why they are useful later on. We're going to use them in the port scheduling application, but essentially that collects all a set of tasks that cannot overlap over time, and they have to be therefore sequenced over time. And so this is a decision variable in a sense, because you are determining the order of these various tasks on a particular machine. And then the rest here is just stating the objective function, which is minimizing the make span, and then making sure that no two tasks running on the same machine overlap. And this is a global constraints, and then you have the precedent constraints. So that gives you an idea of the level at which we model these problems. And you're going to see that the model that I'm going to show you for port scheduling is not going to be much bigger than this. It's going to be more complicated, of course, but not much bigger. So behind the scene, how does the system solve these problems? It's basically a combination of branch and pruning. Pruning is reducing the search space. We have an explicit representation of the search space in a constraint programming system. Every variable, we know that they have a set of variables, and the constraints are removing as many infeasible values as possible, obviously without removing solutions or optimal solutions. And then the branching is simply decomposing the problem. So this is the way inside the system. Once again, I'm simplifying things to some more complicated modern system. But this is the domain stores, and this is the essentially a yeah, can you mute yourself, please? Yeah, thank you. So you have an explicit representation of the search space, and around them you have the constraints, and the constraints don't interact with each other. They are looking at this domain store independently, and they synchronize through the domain store. And so constraints is essentially, in a first approximation, I will revise that later on, is feasibility checking if the constraint can be satisfied. And if it's feasible, it's trying to prune the search space as much as possible. And the holy grail is essentially to remove all the values that are inconsistent at a particular point. The way we solve this problem is completely irrelevant. And this is one of the beauty of constraint programming. Some of the algorithms that I've shown you have been improved over like 2 decades, starting from algorithms that were cubic and now are, low linear times. And so linear time. And so this is one of the things which is nice in constraint programming. The problems are very well defined, and therefore they define very nice computational problems that you can solve and improve over time. And they are dedicated to every one of the constraints. So let me show you this simple example here so that you get an idea of this propagation. I will reuse it later on when we do learning. And therefore, I just want to go over it quickly. So this is 5 variables there. 4 of them have to have a different value. That's once again a global constraint. And then you have the sum has to be smaller of the first 4 ones have to be smaller than 9, and x2 has to be smaller than x5. So you start by assigning x1 to 1, and that immediately, because of all different constraints, remove the value 2 for variable x2, x3, x4. Then you have this constraint x2 is smaller than x5. So we push the value, the lower bound of x5 to 2. And then there is nothing that you can deduce. You make a choice here. It's actually a constraint that you add to the system. It assigned the value 2 to x5. Immediately, because of the constraints x2 smaller than to x5, assign the value 2 to variable x2. The all different constraints is going to kick in, remove the value 2 for x3 and x4. And at that particular case, at that particular time, the summation constraint is coming in. The only values which are possible for x3 and x4 are 3, and therefore the all different constraint is failing. When you fail, you go back, you change the choice that you have made, and you make the opposite choice. Okay? So that's how the system is working behind the scene, once again, in a simplified version. So when we go back to Dropshot scheduling, what you have is that the constraints are very big. There are these no overlap or disjunctive constraints. And then you have a variety of precedence constraints. You can have cumulative constraints. You can have sequence-dependent cost and things like this that you're going to see in a moment. And so to give you a sense of what you do in one of these constraints is that you're solving this algorithmic problem. For instance, a no overlap constraints will have the release date, the due date, and the duration of every one of the tasks, and has to determine if there exists a feasible solution. So it's a one machine problem in a sense. And if it's feasible, you want to prune the search space as best as possible. So this is the no overlap constraint, one machine feasibility. No, this is still NP hard. So you typically approximate the way you can view this is that you are using preemptive scheduling, and you can compute that in n log n time. And then once you have that, the next thing you do is to see if you can prune the search space. And the way you do that is that with these beautiful edge finding rules. There are many other rules that we applied, but this is one of them, where you are actually trying to determine if the first task can be after the second and the third one. And in this particular case, you cannot do that because you can see that if A1 is to finish before, the end date of task 2 and task 3, you just don't have this time to schedule all of that. And therefore, you know for sure that A1 has to be scheduled after A2 and A3. And in one step, you push it forward. You update its lower bound in a very significant fashion. That's why these edge running rules are so powerful. They are pushing a number of tasks tremendously, both forward and backwards. And this is a key pruning aspect of constraint programming solver. One of the things that I will talk about a lot in the application are these cumulative constraints as well. You can think of no overlap, but no, you have a capacity. You don't want too many tasks to execute at the same time. They can be weighted as well. But essentially, you want to make sure that, let's say, not more than 8 particular tasks are running at the same time. And this is the way you can formalize it. At every point in time, you see the tasks that you are using, you see the resource that they are, the capacity of the resource that they are asking, and you want to be sure that this is not exceeding the capacity of the resource. And so this is one of the basic tools that we are using as well. There are a variety of pruning rules for these cumulative constraints as well. So if you want to know more about this, there is a very good survey article by the IBM iLog crew. They have a paper that was published about 3 years ago, which summarized most of the progress that had been realized inside the solvers. And so the modeling level, this is all the things that I have been talking about, these interval variables. There is also this concept that I'm going to use in a moment, which is called optional interval variables. So these are interval variables that may be or may not be present in the schedule. You can choose if you're actually executing that activity or not. And this is very nice modeling tools when you have different resources that can actually do something and you don't know which one is going to do what. You have the sequence constraint that I just mentioned, and then you have a wide variety of constraints. So some of them are listed here. One of the things that you're going to see in this talk as well is the sequence-dependent transition times, which can be expressed at a very high level again. And you have other things like calendars and things like that, where you can see that workers cannot work on a weekend, or they can only work 50% of their times, and so on and so forth. The solver level, this is where a lot of progress has been realized. And I won't go into all the details, but I can tell you that the progress has been realized on almost every aspect of the solver. So the lower bounding techniques, you have temporal and linear relaxation. So the solver will choose what kind of relaxation is good for a particular problem. At the level of the primal solutions, you use large neighborhood search to improve solutions, to get better and better solution. You also use restarts to make sure that you randomize the search and try to explore different parts of the search space. Now, when you do restarts, you also use these no goods for the search, such that you don't explore the same subtree twice. This is one of the innovations that this solver has introduced, let's say more than a decade ago. And then what is done at this particular point is that the system is trying to see what to focus on. If it's focusing on the primal solution or the dual solution at every point in time. And they switch the type of search that they do at different point in time, just when they think that, hey, this looks like, we are close to an optimal solution. So these are all the techniques that have been improved in the last 10 years. So let me show you an example of all this in practice. And this is something that has been done by one of my former students as a Fulbright, Damla. And this is going to be of a case study in Turkey. And so this is about port scheduling. Most of you probably have seen these massive containers. They are very, very impressive. And when they come to a port, you have to offload and load some of these containers on this big ship. And this is the general configuration of a container. You can see that in various countries in Europe. So you have the seas here at the bottom. This is the port itself. You see the various ships there. And this is the yard. This is one particular way of organizing the yard, where you have the yard cranes. And so the goal, obviously, is the ship is going to have to be positioned on the quay. There will be these quay cranes that are going to unload and offload the containers. They are going to be brought by these yard trucks that I'm going to show you in a moment to the yard. And the yard cranes are going to put the containers at the right place. Okay, so let me show you some of these things. So this is a quay crane. This is the most expensive and the most delicate equipment to port. This is typically the bottlenecks in most of the ports, at least in Europe. And once you are on top of one of these things, it's kind of scary because they move like crazy when there is wind. But this is the key things that you schedule around. This is a port in I don't know where it is, but you see a bunch of these quay cranes in a row for offloading and loading this ship. This is the yard cranes. This is the same thing, but the yard side for loading the containers in the yards. That's where you store them. And so you can see another versions of them. And then you have these trucks that are moving between the quay and the yard, taking these containers one at a time and moving them at the right place of the yard, while the yard cranes can actually deal with that. So this is the general operations that you do in a container terminal. So you start by what is called a berth allocation problem, finding out where you put the ship. Then you do the quay crane scheduling. So you allocate what the quay cranes are going to do. Then you have these yard cranes dispatching. So that's how you schedule these trucks everywhere. Then you have the yard crane scheduling and the positioning on the yard, which is you have to decide where to position this container. And so typically, I think when I worked in Europe on some of the industrial problems in this field, the way people were doing it is by sequentially solving every one of these problems. They will do the berth, then the key crane assignment, then the yard truck, and so on and so forth. And what I'm going to show you, and so when you do that, you leave a lot of opportunities for optimization on the table. And so what I want to show you today is an integrated approach. We're going to do everything at the same time. Okay, so we're going to solve the problem globally using constraint programming. And so, this is for a medium-sized port. So that's the case study in Turkey. And you see one of the ships there on a key crane and so on. So this is what we're going to do. So this is the problem. So the ship is coming. And then one of the innovation here is going to be the fact that we are going to deal to a large extent, not completely, but with shipments. We're going to say these shipments are going to a certain place. We handle them, together, and we choose the place on the yard and we move them to the yard. And so that's the various shipments. And obviously we'll do not only offloading, but then loading them on the ship as well. And so that's what is happening there. So you basically choose where the shipments are going to go and, how the cranes are going to manipulate the shipment. So it's a larger unit than the container. And then the key cranes are going to basically deal with these containers at the yard level. And every one of them is going to choose where to put them, and you will have to schedule them because they have to do the work as well, and they're different positions and so on. And you have multiple ones as well. So the one thing which is complicated everything is that these key cranes are big, bulky, equipment, and they cannot cross each other. So if you move one and you want, for instance, this key crane to be there, the other one has to be at a certain safety distance. They cannot be close together. Otherwise, it's very dangerous because the containers could bump into each other. So if you want this key crane 2 to actually go into the key bay number 3, you have to make sure that you push key crane number 1 to location 1. So in a sense, when you have different key cranes, you know where they can be located, what they can serve. Some of the things are going to be allocated to them uniquely, but some of the bay location can be served by multiple key cranes. And so that's some of the constraints that you have to deal with. Okay, so these interference constraints. And there was some beautiful modeling of this by people in Montreal that we are going to reuse, but in a constraint programming context. So let me show you now at a very high level what the model is for a constraint programming system. And so this is the model that you see. This is the simplified model. I'm just ignoring currently the yard trucks. I'll show you the full model in a moment. But this is the size of it. And as I promised, is not that very different from the size of the Dropshot scheduling. Of course, it's more complicated. You have a larger number of no overlap. You have this alternative constraint that I will talk about in a moment. You have the precedence constraints there. But roughly speaking, this is the size of this model. Now, I have to tell you that it took us about a year to come up with that model. But when you look at it, it's very small. Right? And you see the decision variables on the left-hand side, which are mostly interval variables everywhere and sequence variables. So let me go over a little bit of these things with you. So the first two variables are going to be very natural for you, right? So for every one of the shipment, we have to decide which key crane is going to deal with that. And what is the time that key crane is going to handle that equipment. So this is what you see there. This is the starting date and the end date of the key crane task of that particular shipment. And this is the yard crane schedule. Now, obviously, we don't know which key cranes are going to do that. And so that's a decision variable. And that's what you see there. These are the optional variables. ING is container I, and INJ, and J is the key crane J. And so you're deciding if actually container I is going to be dealt with by key crane J and over which interval of time. And obviously, these two tasks at some point, if J is actually is handling container K, they have to have the same starting and end date. So that's what you see there. So you basically say all these optional variables, one for every container and for every key cranes, and the same thing for the yard. That's the pure decision variables that we deal with. Obviously, we have to have no overlap constraints over those, but you have also some time-dependent travel times. Well, you have also sequence-dependent travel times there, because you are basically dealing with some of these containers and you have to go from one position to another one. So it's a no overlap constraints, but in between you have a certain distance because you have to move to the next container. So you have a nice generalizations of these disjunctive constraints where you have actually distance between the various activities there. The precedence constraints are interesting because you don't deal with them at the shipment level, you deal with them at the container level, because you move this shipment all together. And so the key crane has to be synchronized with the yard crane. It's going to take some time to go there. But once you start, with the first container, you're going to follow the other ones afterwards. So it's kind of a nice, precedence constraints there, which work at the level of the containers, but is expressed in terms of the shipments. And then you have these interference constraints, and the way we model them is once again by taking all the various tasks that can overlap in time, that cannot interfere, and we are basically saying that they cannot overlap in time with this particular safety distance that you see there, the time that they have to move. Once again, I don't expect you to understand all the details. This would take hours to get to all the details, but that gives you a sense of what the model looks like. And so this is the objective function, which is the weighted completion times of every one of the vessels. Because in a port, what you want to go is to handle as many vessels as possible. Once they come in, you want to basically make sure that they are dealt with as quickly as possible, that they are processed as quickly as possible. So this is the full model. When you have the yard trucks, it gets a little bit more complicated. There are a little bit more decision variables, and you have to deal at the container level for some of them and synchronize the container and the shipment level, because the trucks are only manipulating one container at a time. But this is the way the model is done, and it is a generalization of what I've shown you. So let me show you some of the results because they are very compelling. And this is on the simplified model because the MIP cannot solve the big ones. And what you see there is the results in the objective function, the average CPU time, the optimality gap between the MIP and the CP solvers. And what is interesting is that this superscript there that you see, when you see something like 4 and 1, it basically means that here for this instance with 8 base and 25 shipments, 4 of them cannot be solved by, 4 instances cannot be solved by the MIP solver. And only one of them can actually be solved one of them cannot be solved optimally. So in this particular case, the MIP solver cannot solve anything optimally. You can see that the CP solver can solve all of them optimally in this particular case. So what is interesting is that the improvement in computation times is very substantial for the CP solver, and also the quality of the solution is much better, because almost always you can either solve the problem optimally and prove optimality, or you are very close. And there are only a few instances where you cannot do that. This is the time you see most of the time the MIP solver is hitting the limit. You have to solve this problem in a reasonable time because, before the ship is coming. And so you can see that most of the time the MIP solver doesn't get into the limit and cannot, solve most of these problems. So that's giving you the sense of what the constraint programming solver are doing here. And one of the things that I want to emphasize again is that we are basically solving these problems in a global fashion. We are taking all these sub-optimization problems and solving them globally, which is something that could not have been done, let's say 10 years ago. No, I'm not saying that you can do that for all the ports. Rotterdam would be really big to do in this particular fashion, but you could have some decomposition where some of the sub-problems can be solved globally. So that's the first part of the talk. Let me talk a little bit now about hybridizing constraint programming and MIP. And this is a problem that was done with one of my PhD students back in Australia, Eddie Lam. And this is a branch and price and check model for a combinations of routing and scheduling problem. And this was motivated by application with the Australian Air Force that were running a lot of logistic and military mission in the Asia Pacific region. And so what I want to talk to you about here is these combinations of constraint programming and mathematical programming. And one of the trends in combinatorial optimization has been moving to this techniques which are called branch and check or logical Bender's decomposition, where you basically generalize Bender's decomposition with sub-problems that are non-convex. And they are typically very combinatorial. And so what you have to do is to generalize, solve these problems first, which are highly combinatorial, and then generate new kinds of Bender's cut. And so what I'm going to show you is these combinations of branch and price, and then Bender's decomposition, but a combinatorial Bender's. And what I hope that I show you here is this beautiful synergy between mathematical and constraint programming. So what is the problem? It's a VRP problem with scheduling constraints, essentially. So you have multiple vehicles, they have pickup and delivery constraints, They have time windows when they can do these pickup and deliveries. And what they have are these capacity constraints as well on the vehicles, but they have also these location constraints. At some point when they visit a particular location, they are capacity constraints on that location. Either how many people you can serve at how many requests you can serve at a particular time, on how many people at one particular point in time can be at that location. So think of it as the number of parking slots at an airport or the number of landing and takeoffs that you can do in an airport. So this is the idea. So in a traditional VRP, every one of these nodes is a request. And when you move to what I'm talking about here, every one of these nodes is a location. And at that location, you may have multiple requests, but you have constraints on these requests. You may be able to serve 2 of them at the same time. Let's say these 2 or those 2, but not more. So you have these capacity constraints on these locations. And this is a problem that I'm encountering more and more. So we are working currently with autonomous truck. And this is one of the problems that you will have, is that between the first mile and the middle mile, you will have these transfer points, and they will have these presence and service constraints. So humanitarian and military logistic, city logistic, and no automations are typical problems where you have these constraints. And so the way we approach them, this is a very high level view, is that we solve a master problem which works at the level of the routes. And then we send these dual variables, we get routes. At some point, some of these routes are going to be converging to a high quality, the column generation is going to be converging. Then some of these routes are integral. And what you have to do is to see if you satisfy these scheduling constraints. If you don't, then you send a Bender's cut to the master problem and you start the column generation again. And at some point, some of these integer routes are going to be feasible, all of them. And then you have both a route and the routes and the schedules. And that's what we are going to do. That's how the problem is going to be solved. Now, this is the master problem. For those of you who know column generation and routing, this is very traditional. You reason at the level of the routes. You have to cover every one of the pickups and deliveries. And what I'm hiding here are the Bender's cut that I'm going to explain in a moment. Now, to generate the routes, you really use the traditional techniques. It's a resource constraint shortest path that you solve with a labeling algorithm. Nothing to see there. This is very traditional. What is interesting is the sub-problem, the Bender sub-problems. Now you have a set of routes that are integral. They are your master problem is selecting them, and you have to find out if they are feasible from a scheduling standpoint. And that means that you have to find, starting and ending dates for every one of the visits that they do at the various locations, such that they don't exceed the capacity constraints at these various locations. And so this is the sub-problem, which is highly combinatorial. You have to start the arrival date and the departure date of every one of these vehicles. You have to make sure that the routes are satisfying, obviously the distance constraints to move from the successor, from a particular node to its successor. And then you have these cumulative constraints that I mentioned before, right? So you cannot exceed the number of planes, let's say, at the particular airport, or the number of trucks at a hub cannot exceed the capacity of that hub. And so that's the cumulative constraint that we have there. Now, if you find that this is feasible, great, you're good. But if you're not, what you have to do is generate a Bender's cut. What is this Bender's cut? This is obviously not a convex problem. So what you do is that you have to find a way to exclude the fact that these routes are not compatible. They cannot be scheduled such that you don't satisfy the cumulative constraints, the location constraints at every one of these nodes. And so what you do, and this is the combinatorial cuts that you can generate there, you have to say that the arcs that you have in these routes cannot be all selected at the same time. So it's a very simple no good, but in a sense, it's a very nice no good because it only reasons about the arcs. It doesn't reason about the time. And so this is what is nice. You basically add these Bender's cut, and then you continue the process that I've shown you. So in a sense, you do the master problem and the pricing problem, that's the column generation. You have this separation here to find out if the routes satisfy the scheduling constraints and generate this Bender's cut. And then when there is nothing else to do, you branch. And the branching is also interesting. You branch on sub-routes, but I won't go into those details. So I'm going to compare that once again to MIP, CP, and branch and price and check. And the comparison is going to be very easy, as you're going to see. Because essentially, when you see MIP and when you see CP, there is almost nothing that they can do. So these two techniques have to work together to actually solve the problems. And so when you see, see at the middle, this is an interesting data set. You can see the quality of the solutions that you're generating there. This is a number of no-goods that we are generating. This is the gap, the optimality gap that we have. Now, this gap is obviously one of the things which is nice about these gaps is that most of the well, I don't know if it's nice, but this is the reality. Most of the limitation is at the lower bounding part, because you can see that here, the best solution is when you relax here the capacity constraints, you have a best solution of 793, and so most of the gap here is at the level of depends on the quality of the lower bound, not the primal feasible solution. So this is another one that I like a lot. So you can see here that you generate a very large number of banders cut, but you converge to very high quality solution very quickly. And so this is what is nice about this problem. So once again, this is something where the combination of CP and MIP can actually solve these problems that could not be solved otherwise by these two techniques individually. The one place where the CP solver is very good is proving infeasibility. If you have only a capacity of 1 or 2, the CP solver can show that this is impossible. So that's what I wanted to show you there for hybridizing constraint programming and MIP. So I want to move to the third part of the talk, which is this next generation of constraint programming solver, which are very complementary to the one that I have used so far, which are based on learning. And so this is, so if you want to learn about this, this is probably the best paper to read. This is by some of my former colleagues at NICTA in Australia. And I'm going to go over some of these techniques in a moment here. So the key point here is that this is a quote by a Spanish poet, which I like a lot and which is very relevant to a lot of context. But what you don't want is to actually rediscover the same thing over and over and over again in optimization problem. And interestingly, most of the solvers are actually suffering from this. And so this is a very simple graph coloring. And if you use a simple CP solver, you're going to have 500,000 failures. But if you learn, and I'm going to tell you what learning is in a moment, you have only 18 failures for solving this problem. Same thing in scheduling, and I will show you, real benchmarks in a moment. But you can move from about 1 million failure to about 1,000 failures. So you're basically reducing the number of failure by 3 orders of magnitude, which is kind of remarkable. So let me tell you what this is. So the key idea is that what you want to do is to learn from failure. And this is so when you fail during your search, you want to learn something interesting from that failure. And so this is a long history. Actually, the first, scientific talk that I attended was talking about this. And that was back in 1986, a long, long time ago. But it really didn't work until the last, 10, 15 years. And this is this, and what I'm going to talk is this technique, which is called conflict-based learning, where you learn a particular clause, which is of a certain shape, which is the 1UIP, when you encounter a failure. And I'm going to tell you what this is. But to get to there, I need to tell you that implicitly in a constraint programming solver, you have an inference graph. You are making deduction, and you can actually store explicitly or implicitly this deduction. And mostly what you do in a constraint programming solver is updating the bounds or saying that a value is a variable is equal to a value or is different from a value. And then you can record inferences based on the constraints that, for instance, if I have a constraint that x is greater or equal than y, and if x is smaller or equal to 2, then I can deduce that y is to be smaller than 2. So this inference, I can actually record in an inference graph. And you're going to see why this is useful in a moment. So this is a graph of a very simple example that I used in the earlier part of the talk. So these are all the deduction that the system has done until it deduces that the system is in a failure state. And so what the learning is going to do is very interesting. It's going to go from the failure back to the choice point that you have made. And what you want is to find all these literals, these things that we have deduced, this inference that you have deduced. And you want basically to go back to a point where all of them but one are before the choice. So such that you can explain the choice, the mistake that you have done as effectively as possible. And that's what is called a UIP. So, these are the two things that explain that this is false and this is really boring because these two variables have to be different. But now you go back in, you go back in this graph until, as I told you, all the choices, all the literals that are explaining these failures are on the left side of this choice, except one. Okay, so you need one because you want to know what the choice has been responsible for. And so at this point, you have a no good. This is a one UIP no good. And this is how it looks like. It tells you that I have a failure if x3 is smaller or equal to 1, x4 is smaller or equal to 1, and x2 is different from 2. And this no good is really intriguing because it has nothing to do with the choices that you have made. See, the choice that you have made is x1 equal to 1, and x2 is smaller or equal to 5. But it really captures something fundamental about, about what the problem is. It's an implicit, constraints of the problem. And what this learning is doing is revealing it to the solver, and now you can put it inside the solver and make sure that you will never have something which has exactly the same conflict. And so this is what you are doing now. Every time you are failing, you are also using the constraints to actually infer new constraints that you can put inside the solver. So the role of the constraints, instead of doing only feasibility and domain filtering, as I've told you before, now you have to explain your failure and explain why you are making deductions. And you are using them to deduce no goods or implicit constraints, which are really making a huge difference, as I will show you in a moment. So this is, for instance, what you do for explaining the cumulative constraints that we have used in the port logistic problem and that I mentioned before. So what you really look at is this overload. At some particular point, a resource is overloaded. There are too many tasks using it, and you want to be able to explain why you have this failure, and to make sure that you don't repeat that. And a key concept in doing that is this compulsory part. So if you have this task which starts here and can finish at the latest point there, you can move it, and it can be in these intervals. You don't know where, but you know that it will actually be scheduled in between 5 and 6. And so you know that this task has to be executed there. So when you look at explaining this, one of the things that you can do is to say, hey, if I have these bounds for these 3 tasks, then I know that I cannot go back in that situation again. And so you can say that the no good is that if E is ranging between these 2 things, D is ranging between these 2 things, and C is ranging in between these 2 things, I will have a failure. But this is a very, very poor no good. So you want something that is actually generalizing much better. So one of the things that you can do is that you can say, hey, I just want to look at this compulsory part and where there is an overload. And once you have that, you can start, saying that there is a wider range of domains for these interval variables in which you have this failure. And therefore, you increase the no good becomes more general, and therefore it's going to prune the search space better. And you can even push this further. You don't need all these parts. You need only one point where they are actually in conflict. And once again, you are able to increase the range of these decision variables. And the no good is much more general and give you a very nice way for actually generalizing the failure and making sure that you don't repeat the situation down the lines. You do the same thing for the explanation, for actually explaining the inferences. You again look at different points and you decompose the points such that you actually know exactly how to explain the various inferences. And so this is the value of learning. So if you look at these very complex problems like resource constraint project scheduling, the RCPSP max, most of, when you are starting using learning in this particular way, a lot of the open problems that were like open 10 years ago now have been closed. And most of the time you solve these problems 2 orders of magnitude faster. So for some of these problems, I'm not saying that this is valid for all of them, but especially for problems with cumulative constraints, these learning techniques have a really big impact in practice on solving these particular problems. So this is what I have done so far. So I basically review some of the progress that have been realized in the last 10 years. And what I want to talk to you about is a little bit what the future can do. And obviously what I want to do there is to look at ways of combining machine learning and optimization. And so this is a paper that we published earlier this year, where we try to use machine learning for approximating Dropshot scheduling, using techniques which are combining both machine learning and optimization theory. And so what we are doing in that field, and we are doing that in a variety of domains, is trying to approximate optimization algorithm using machine learning. So we want to learn the input-output relationship of an optimization problem. And so we have the input of the optimization problem, we have the output. And what these optimization proxies are going to do is having one step, which is predicting what the solution can do using a deep learning system, and then using optimization for restoring feasibility, because most of this is a regression task. So typically you don't have a feasible solution. So for instance, in power system, we had a lot of success doing this. And this is what you would do. You would say, hey, this is the net load of your system, and this is how you have to set up all the generators. And you just, and these are the constraints that you have to satisfy. They are typically nonlinear, but you are really interested in learning this mapping between input and output. And so the challenges when you try to do that is that, contrary to computer vision or natural language processing, for instance, here you have to deal with a variety of physical engineering or business constraints. It's what is called an empirical risk minimization, but under constraints. So it's a challenging machine learning problem because of that, because you have these hard constraints that you need to satisfy. But one of the beautiful things here is that, data is not an issue because we have an optimization solver. We can generate as many instances that we want, solve them using the optimization solver, and then we can learn from those instances that we have solved using the solver. So you have these very nice synergies also between optimization and learning. For instance, the learning algorithm that we use is based on Lagrangian duality to actually use the constraints as best as we can. So let me show you what we can do in Dropshot scheduling when we try to approximate Dropshot or kind of learn the solution of a Dropshot scheduling. What we typically do is that we have this deep learning system which are adapted to the structure of the application. So in this particular case, you see the job layers, you see the machine layers, and you can see these first layers in the deep learning system as encoding information in the jobs and the machine. And then afterwards you have the share layers which are doing the regression itself based on the encoding. And then afterwards, obviously, it's a regression task, you're going to predict the start times and so on, but they are typically violating some of the constraints, typically minimally because we are using this Lagrangian dual approach to the learning problem, but still they violate more, some of the constraints. And so what you can do is use the solution here, use the guess and impose the precedence constraints that are derived by the solution and try to minimize the make span based on the constraint which are implied by the machine learning approximation, the optimization proxy. Now, this is not guaranteed to be feasible, although we never found an instances where this was the case. And obviously, this is a problem that can be solved in polynomial time. But sometimes it's potentially possible that this is not actually solvable because there is a cycle. And then you can use a greedy approach based on the prediction of the machine learning algorithm if that happens. But as I said, this never happened in practice. So in a sense, what we can do is machine learning, which is going to take milliseconds. Then we can solve this polynomial algorithm here for solving this problem very quickly, and we have an approximation to the optimization solver. So what I'm going to show you is this experimental setting. You are on the floor and you observe that the machine now is slowing down, and you want to say, hey, I want to reschedule this very quickly, all my job very quickly, to take into account that this machine is slowing down for some reason. It needs maintenance soon or something like this. And what we are trying to do is to see how fast we can actually, whether the machine learning algorithm is going to be able to reschedule this almost optimally in, let's say, milliseconds. And so we are going to train this with an optimization solver, which is given about 30 minutes of time. And we'll also compare to some of the heuristic that you can use in that particular setting. And so these are some graphs that show you how well this machine learning algorithm, this optimization proxies can do. So this is a state-of-the-art solvers that I mentioned previously. And one of the things which is really nice here is that in about a couple of milliseconds, you can actually give a solution which is better than the optimization solver after, let's say, 30 minutes. So, there is some randomization in the solver, obviously, but this is the mean average of the time that the quality of the solution over time. Sometimes, obviously, it doesn't do that. The optimization solver is better, but it takes a long time to get better and to get to the same quality of solution. This is a case where the machine learning algorithm is almost as good as the optimization solver after 30 minutes. Once again, it takes a long time before the optimization solver can actually get the same quality as the machine learning algorithm. No, once again, the machine learning algorithm is seeded with the optimization solver, right? So it's this nice combination of machine learning and optimization. These are very general results on some hard instances in Dropshot. And there are a couple of things that are interesting to see here. So first, you can see that the prediction errors is typically very, very small. And the constraint violation are very small as well. So that's one thing that you want to see. You can also see how long, on the right-hand side, you see how long it takes for the optimization solver to beat the machine learning approach. And that range from about 12 seconds to 30 minutes. Some of the times the machine learning algorithm is better than the optimization solver, even taking milliseconds compared to 30 minutes. The real thing that I think is really nice is the fact that it's much, much better in terms of quality than the heuristics. So if you want a solution very quickly, because you need to reschedule your shop, this is one of the ways to do this. You learn offline, and then you use this machine learning and then the repair optimization for actually finding high quality solution. So let me conclude now. So this is what I wanted to tell you about today, the state of the art in scheduling, how it has improved in the last 10 years, the opportunities for hybridizing constraint programming and MIP, which is a very exciting approach. I believe the ability of constraint programming solver now to learn from failure, which for a variety of applications is really the way to go. And then this idea of actually combining optimization and machine learning for solving some of the problems that you need to solve in real time when you really need to have a solution extremely quickly. So this is what I wanted to tell you today, and I'll be really happy to answer any questions that you may have.
Okay, thank you, Pascal. It was really marvelous. And now I allowed everybody to unmute himself or herself. So if you have any questions, don't hesitate and just ask. And before you do it, maybe I can ask the first question. You have also mentioned local search techniques in CPU optimizers. So I think that this has a remarkable impact on the quality of those solvers. Could you mention a little bit?
Yeah, so most of the solvers now, and this is what we use all the time, right? So use what we call large neighborhood search. And the key idea is that once you have a good solution, you fix part of the solutions and you free the rest of the variables. And then you try to re-optimize using the same solver. And this is why this is so nice, because it's completely generic. You fix a part of the solver, and that can be dedicated, right? So, but you fix a part of the solution, and you re-optimize and try to improve the solution. You know, the solvers that I mentioned earlier today are doing that systematically, and this is how you get really, really good primal solutions. Because as soon as you find a solution, you start this large neighborhood search, and it improves the quality of the solution tremendously. So this idea of large neighborhood search is very powerful. What typically the constraint programming solver are using is using the structure of the constraints to do that relaxation, choosing which constraints to relax or not. They can be all the constraints on the machine, or they can build a precedence graph and remove part of that precedence graph, remove some of the precedence constraints that have been added. And you can do that for cumulative constraints or producer-consumer relationship and so on. That's what the system does. It's a critical part of the success of this solver. That's how you get very good primal solution quickly. Yeah, very good point. Very good point.
Okay, thank you. So Ernst, please go ahead.
Yeah, thank you very much. Pascal, thank you very much for this really informative talk. My question is, in the examples, it was around, I think, slide 40 something.
Yeah.
The example showed that for the machine learning thing, you were using specific examples, that is, specific parameters for the times and what have you. Now, this, of course, challenges the question, if you want to have an algorithm and judge its complexity, you should actually include the time for the ML part.
Oh, yeah, absolutely. Well, I think the way to view this, let me phrase it this way. So, I'm going to give you an analogy of what we're doing in Power System, right? So the way power systems are working, and there are very lot of similarity for the problems that I worked in the past in manufacturing, right? So you typically divide things in strategic, tactical, and operational planning, right? And so in the power system, for instance, you decide which generators are going to be on for the next day, the day before, at between 11 and 12. At that particular point in time, before operation, you have about 12 hours. In those 12 hours, what we do is we do machine learning. So we run a large number of scenarios, and we learn what can be the operational problems for the next day. So we basically generate a reasonable distribution based on the forecast that we have, on all the problems that we can have in the next day. And we train the machine learning, and we have about 12 hours to do that. And then on the day of the operations, we have all these machine learning models that are ready to help solving, let's say, stochastic optimization problems. I think you can do exactly the same thing, and that's what we are doing right now in the context of manufacturing and application in scheduling. The day before, you basically say roughly what's going to be happening in your floor on the next day. You can train the machine learning, and then you apply them in practice. So what we are doing in this particular case, and that's the answer to your question, right?
No,
is that
not the answer to my question.
We are separating the learning from the operation, right? The learning is taking place before, and the other one is
okay. I don't mind that. But what I'm trying to ask you is if you add up the things.
Oh yeah, it's going to be longer. It's going to be longer. Oh yeah, it's going to be longer. It's going to be longer. Obviously, it's going to be longer because you are solving a lot of instances. But the key point here is what we are trying to do is to solve, and I'll give you another answer afterwards. But what we are trying to do is to solve a problem in real time that we cannot do really with the optimization solver, because the optimization solver is not fast enough. And that's what we are trying to do. So I'm not trying to say that we are replacing optimization. I'm an optimizer by training, right? So, yeah. And therefore, I'm not trying to say that, I want to replace optimization by machine learning. I don't believe that. I think this is a combination of the two, which is really interesting. And in that particular case, I'm trying to do something that the optimization solver cannot do. So let me give you another example. I hope to convince you with this example, but this is something that we do in transportation.
We don't have to waste time on that because you don't have to convince me on this. I agree with you.
Great. Fantastic.
So that's not the problem. I sent you another question which on the system, which you might want to answer or not. But the basic question was really about sort of what is the whole complexity.
So I mean, all the problems that you have are NP hard, that in practice are NP hard in general, right? So the key point is that you have to find out how difficult they are and how difficult they are for different techniques, right? So there are two generations of solvers now, and some of them are better for some application, let's say when it's really a disjunctive problem, and some of them are much better for, let's say, a cumulative problem. And it's very difficult currently to tell you why they really work. I spend a lot of time looking at traces of what these algorithms are doing. And it's extremely difficult. I think they generate, for the cumulative problems that I've shown you, they generate millions and millions of no good. And these no goods make no sense, really, when you try to analyze them. But what they do is that they have a tendency to focus on a region of the schedule which is difficult and generating interesting information about that region of the search. But trying to tell you how many no goods are going to be generated and what is the shape and what they really capture is something that we have not been able to do. And so, it's very difficult to answer your question. It is very, very difficult.
I agree with what you're saying. But the problem to me is it's not clear what from these different heuristics, what the effect on the complexity of the problem, on the algorithms then afterwards, like MIP or whatever is. And I think you just did not cover these.
So let me tell you one other thing that I think is a big advantage of constraint programming compared to MIP. Okay, and let me give you some intuition of how I typically approach the problems, right? So one of the things that constraint programming, so when I talk to industry, I tell them always, if it's scheduling, if you can write a MIP model, solve a MIP model.
It's not necessary, again, as I said, to waste the bandwidth for this. I know what these whole things are. So, and I think I believe in them as much as is necessary. So don't try. I mean, I'm convinced as much as possible.
So the one thing that I want to tell you is that one of the beauty of the constraint programming solver is that they don't discretize time. And therefore, if the granularity of your time is very important, the MIP model may have just too many variables. So the way the MIP solvers are going to be good in some of the application where constraint programming is not good is when you can model the problem as a flow. And so if your flow is nice and reasonable, even if it's a multi-commodity flow, then the MIP solver is going to be good. But if you have to discretize time and have a time index formulation, you are probably in a very difficult spot in general. And the constraint programming solvers don't have to do that. They don't have to.
Guys, I love your discussion, but I'm sorry, I have to give floor also to other people. So Taha Arbawi, please go ahead.
Thank you, Pascal, for the very nice presentation. So I was interested in the data augmentation that you talked about. I have tried to do the same thing, so learning on real-world data, but usually when you work with industrial partners, it's very hard to find such amount of data. So what we did is that we randomly generated the data, but it's not always the nicest idea that you can get, because usually these data are not are so randomly generated, and they may not be really faithful to the real world data. So how can we deal with that? Thank you.
Yeah, so there are two things that I can tell you. One which you're not going to like, and the other one that you may like. The first one is that, I mean, if you don't have a really understanding of what the distribution of the practical instance are, it's very difficult to do any real work on those. So what typically we try to do is to work with the partners, get a sense of what the distribution looks like, and then generate synthetic test cases that resemble that. That's number one. Even if you do that, you have to be very careful on how you generate data, because the solvers are randomized. They can generate very different solutions to very different problems. And so we have a paper just about data augmentation and saying how you should do data augmentation when you want to use machine learning. It's a very important issue. Because you don't want to do just generating benchmarks randomly, because they have different, they may have completely different solutions, and they may have that may complicate the learning problem tremendously.
Yeah. So what we learned is that the outcome of the learning algorithm is very, very dependent on the data that you generate. So if you're not careful with that, that might give you some results that are good when you test them, but in the real, on the shop floor, they don't really work.
I agree. I mean, the quality of the data is good, but one of the things that we have as a big advantage, let's say compared to computer vision, is that we can generate the data. We can use the solver. We have the solver. We have the ground truth, and that's what I like about these optimization proxies. We have the ground truth, and that's a unique aspect for machine learning. We have a lot of complications, but we have also a big asset, is that we have the ground truth, and it's not noisy.
Yeah, are there any approaches on how to transfer the learning that you can do, for example, on synthetic data that you can generate for example, available benchmarks that we researchers use, and apply that and be sure that when you transfer that to practical problems, they might at least work not as good as on the synthetic data, but at least they work very good?
So not that I know of. This is an area that some of my students are looking into, but we don't have results right now. It's a very interesting question. I don't have an answer to that.
All right, thank you.
Okay, guys, thank you. So Mike, please go ahead.
Thanks very much for your fantastic talk. Let me ask you a little bit. I've seen only examples of constraint program on non-preemptive problems. Suppose you have preemptions, and which you do have in practice once in a while. By the way, mathematical programming also will get into a disadvantage then, because the number of variables starts exploding also. But first of all, do you know of a very nice application of preemptive scheduling where you have shown how constraint programming performs, and how do you expect you have convinced me that in non-preemptive scheduling, that constraint programming typically beats mathematical programming. How will it be with preemptive scheduling? The funny thing is about preemptive scheduling is that very often preemptive scheduling is easier than non-preemptive. Not always, but often. And certain heuristics will work reasonably well. In your comparisons, or do you already have some experience, or what do you expect when preemptive?
So Mike, very good questions. I think I have only one problem that I remember where we have results, and they were nice, but I need to find out where they were. I don't remember, on top of my head. I think there are two things that I want to say to address your question. First, all the algorithms that we have are essentially working in that particular context, because most of the pruning algorithms are based on this preemptive relaxation in a sense, and therefore the pruning algorithms are going to be even better because now they will be exact. So that's one of the things that is nice. The second thing which is difficult is that as soon as you have preemption, it's not about orderings anymore. It's about starting times and when you restart and so on. That's going to increase the complexity for the search procedure. And so that may be more complicated. So what I can try to do, Mike, is just go back to these applications that I seen where we were using non-preemption and try to see if there was a comparison with MIP. I don't remember. But I will get back to you. But I think there are these two aspects. One of them is definitely an advantage for constraint programming. The other one is not an advantage, because now you have to reason. You cannot reason about sequences anymore. You are reasoning about when do you actually start and restart a particular task, and that's more complicated, obviously. So it's a great question, and I think you're entirely right. And in practice, you can do some of these things. But I don't remember exactly what we did in that space, so I need to go back to that. Okay. Great point. And great opportunities in that space, obviously.
Rubin Bey, may I ask you?
Hello, yeah, thank you for the opportunity. So Professor Pascal, it's a very nice talk. I really enjoyed it. I never used constraint programming. I used the machine learning. I used integer programming, mixed integer programming myself. We are actually working on the port scheduling problem that you showed. I actually read your paper as well. So I want to ask you about the practical situation that we are facing. So in your problem, it sounds like you have a deterministic optimization. So where you have problem parameters are given before the problem solving. So all the secrets, but more about the processing time of different containers. So that is something that you kind of like assume to be available at the beginning of the problem solving. In a real life problem, and we are facing some uncertainties, some small, some bigger. So my question is, if we have some level of uncertainties in our problem parameter, I wonder whether the same system or same algorithms or same combination of the different algorithms would still work, and to what degree, because we are really interested in this direction and we want to explore the opportunity in practical applications.
Yeah, obviously, as soon as you do, optimization under uncertainty, you get into another level of complexity. There are some of the techniques that we can do in the constraint programming solvers as well, and there are some facilities in the modeling to actually deal with solving these problems online as the uncertainty is revealed. So you can have multiple scenarios, and you can make sure that they agree on let's say the first level of decisions, and then they can differ afterwards. So you can model this in constraint programming as well. So this is like this, multi-stage stochastic optimization, but you do that over a rolling horizon using two-stage optimizations. You can do things like this, or you can do multi-stages if you want, which is actually increasing the complexity even more. But if you do a two-stage optimization, you have the modeling capability to do that. Obviously, the complexity is going to be much more difficult. But this is something that I typically teach in my constraint programming class, that they can do that. Obviously, one of the things, it's going to complicate the problem, obviously, because now you have multiple scenarios. They have to agree on the first level of decision, and then they can do something else. So the complexity is much more significant. But if this is something that you have in your real problem, you can model them that way. The other things that you can do is use robust optimization, right? So if you can actually increase the length of the variables, the duration, and then once this uncertainty is revealed, you can actually shrink it afterwards. So that's also something that you can do. But once again, this is another level of complexity in solving the problems. You have the functionalities to do it in a typical constraint programming solver. Whether this is meeting the real-time requirements that you have in your systems, and that I cannot comment on. But once again, I think what I would recommend is using something which is like a rolling horizon, two-stage optimization, using these constraints that are making sure that the first level decisions are all the same.
Okay, thank you.
Thank you very much. Thank you.
There is one question from chat. The question is about whether there is other than IBM solver which offer generalization of no overlap to handle sequence dependent setup times.
You can
mention also other solvers than CPU.
I think you can look into the Google solver, which does that. You can look at the solver at Louvain in Belgium. They have things like this as well. So there are a variety of open source solvers that you can use. And they have different technologies that they are using, right? So every one of these solvers is slightly different, or sometimes significantly different, but they all have significant assets for scheduling, because as I said before, this is one of the killer applications for constraint programming. So there are multiple solvers, and if you send me email, I can send you the exact references to them.
Okay, and then there is another generic question with respect to your presentation. We have forgotten to put your slides on web, so we will most happily do it after the talk, right?
Yeah. I mean, the presentation has been done yesterday in a plane, so
yeah. So this is typical that we do it in the last minute, and this time
it was
I connected late
just
and
in time presentation.
We didn't manage it. I will be happy to conclude the session. I have one very sad news. You probably already know it. Gerhard Woginger passed away. Our PC committee voted for the best speakers to speak in this seminar, and Gerhard was ranked first among the suggested speakers. And when I contacted him, he replied, it was like in, I think, September, he replied that he is seriously sick, and it was too late for us. So I'm very sorry, but he will never speak in this seminar. Okay, thank you very much, and bye-bye.
Thank you, everyone.